Good evening, Dr. Phil here. Today we'll be discussing on principles of electricity. Electricity is a form of energy resulting from the presence of charged particles. It can be dynamic or static. Dynamic electricity occurs when there is a flow of charged particles. The flow of electrons is driven by a potential difference, the voltage, through a substance past a given point per unit time, also known as electric current. This electric current is measured in amperes. Static electricity occurs when there is an accumulation of charge. Electrical charge. The SI unit for electrical charge is coulomb. Coulomb refers to the quantity of electricity transported in 1 second by a current of 1 ampere, also known as the amount of charge passing a point when 1 ampere flows for 1 second. Each electron carries a negative charge of 1.60217,657 times 10 to the negative power of 19 coulomb. 1 coulomb can be considered to have a charge of approximately 6.241 times 10 to the power of 18 electrons. Electrical charge can either be positive or negative and is related to the number of excess protons or electrons respectively. A material that loses 6.241 times 10 to the power of 18 electrons will have a positive charge of 1 coulomb, whereas a material that gains 6.241 times 10 to the power of 18 electrons will have a negative charge of 1 coulomb. Electrical power is known as the rate of energy used. Power equals energy divided by time. It is measured in watts. Watts is equal to 1 joule of work performed per second. 1 watt equals 1 joule divided by 1 second. 1 watt equals to 1 divided by 746 horsepower. Watt is the rate at which work is done when 1 ampere of current flows through an electrical potential difference of 1 volt. 1 watt is also stated as 1 volt times 1 ampere. Voltage. Voltage is the driving force or pressure which causes electrons to flow. Voltage is measured in volts. Definition of voltage. Voltage is the potential difference between 2 points in an electric circuit that will impart 1 joule of energy per coulomb of charge that passes through it. Voltage equals energy divided by electric charge, or 1 volt equals 1 joule divided by 1 coulomb. Voltage is also the difference in potential between 2 points in a conductor carrying 1 ampere of current when the power dissipated between the points is 1 watt. It can also be defined as the potential difference across a resistance of 1 ohm when 1 ampere is flowing through it. Measurement of voltage. For direct current, it is measured directly with a voltmeter. For alternating current, as AC waveform is sinusoidal, AC does not have a steady voltage. The mean voltage is 0 as AC has equal deflections on both the positive and negative axes. The magnitude of an AC can be expressed as peak voltage or root mean squared RMS value. In the UK, the domestic main supply has a peak voltage of 339 volts or 240 times square root of 2 and an RMS of 240 volts. The RMS value allows comparison of the equivalent amounts of AC and DC power needed to produce the same heating effect. The formula for root mean square is V peak divided by square root of 2. Electric current refers to the flow of electrons driven by a potential difference through a substance past a given point per unit time. Electric current equals electric charge divided by time. It is measured in amperes. 1 ampere represents a flow of 1 coulomb of electric charge moving past a cross-section of conductor in 1 second. 1 ampere equals 1 coulomb divided by 1 second. A flow of 1 ampere is produced in a resistance of 1 ohm by a potential difference of 1 volt. The old definition of ampere is the constant current which, if maintained in 2 straight parallel conductors of infinite length of negligible circular cross-section and placed 1 meter apart in a vacuum, would produce between these conductors a force equal to 2 times 10 to the negative 7 newtons per meter of length. The new definition of ampere. In 2018, the General Conference on Weights and Measures agreed that on May 20, 2019, the ampere would be defined by taking the fixed numerical value of the elementary charge E to be 1.602176634 times 10 to the negative 19 when expressed in the unit of coulomb, which is equal to A times S, where A equals ampere and S equals second. The direction of flow determines whether the current is alternating current or direct current. Alternating current occurs when the flow of electrons in a conductor or semiconductor periodically reverses direction. The frequency of AC, measured in Hertz, is the number of complete cycles per second. A sine wave illustrates an alternating current. Direct current, on the other hand, occurs when there is a unidirectional flow of electrons in a conductor or semiconductor. AC can be converted to DC by a rectifier circuit. Diodes. Diodes is a two-terminal electronic component that only conducts electric current in one direction, as long as it is operated within a specific voltage level. Diodes are used in rectifier circuits. Resistance. Resistance is defined as the characteristic of a material that impedes the flow of electrons or the opposition to flow of direct current. The amount of resistance depends on the individual properties of the material. It is not frequency dependent and it is measured in ohms. Ohm can be defined as the resistance between 2 points of a circuit in which a potential difference of 1 volt produces a current of 1 ampere. 1 ohm equals 1 volt divided by 1 ampere. Ohm is also defined as the resistance in which 1 watt of power is dissipated when 1 ampere flows through it. Resistors. Resistors are components that add resistance to the electrical circuits to reduce current flow. The resistance of a resistor is the same for alternating current and direct current, i.e., resistance is independent of the frequency of the current passing through it. Resistors can either have a nearly constant resistance over an operating temperature range, or a resistance altering with changes of temperature. Thermistors is a special type of variable resistive element that changes its physical resistance when exposed to changes in temperature. For negative temperature coefficient thermistors, resistance decreases as temperature rises. For positive temperature coefficient thermistors, resistance increases as temperature rises. Voltage-controlled resistors, VCRs. This is a 3-terminal variable resistor where the resistance value between two of the terminals is controlled by a voltage potential applied to the third. They have a resistance proportional to the voltage across them. A flow of electrons through a resistant material generates heat. According to Joule's first law, which describes the relationship between heat energy Q generated by an electric current I passing through a resistor R for an amount of time T, Q equals I to the power of 2 times R times T. Wheatstone bridge and strain gauges. A Wheatstone bridge is an electric circuit that incorporates 4 resistors in a special arrangement to measure an unknown electrical resistance by balancing 2 limbs of a bridge circuit so that the voltage between the limbs is 0. It is used to measure small physiological signals, such as in strain gauges and resistance thermometers. Components include a power source, galvanometer, 2 resistors of known resistance R1 and R2, a variable resistor R4, an unknown resistance R3, and a bridge, which refers to the connection across C and D, which contains the galvanometer. Mechanism of action. When voltages at C and D are equal, the ratios of resistance equal each other. R1 divided by R2 equals R3 divided by R4. No current flows through the galvanometer and the bridge is balanced. If the bridge is unbalanced, there will be a voltage present across C and D. Current flows through the galvanometer. To measure R3, which is an unknown resistance, the ratio of resistors R1 to R2 ACB must be known. Adjust the variable resistor R4 until the ratio of resistance across ADB and ACB is equal and no current flows across CD. Note the resistance of R4 required to balance the bridge. Since R1, R2, R4 are now defined, R3 can be calculated using the formula R3 equals R4 times R1 divided by R2. The role of Wheatstone bridges in pressure transducers, such as in invasive arterial pressure monitoring systems. Pressure transducers measure changes in pressure by measuring corresponding changes in electrical resistance. Strain gauge can either be a foil arrangement or conductive metallic strip. It is located on a diaphragm in arterial transducers. Mechanism of action. The arterial pulsation is transmitted to the diaphragm via a continuous column of fluid. Stretching of the diaphragm occurs with each arterial pulse. The attached strain gauge stretches with the diaphragm. The resistance of the stretched strain gauge increases. When the diaphragm relaxes, the attached strain gauge relaxes with the diaphragm and the resistance of the strain gauge decreases. R3 is the strain gauge attached to the diaphragm. The ratio of resistors R1 to R2 ACB are known. The variable resistor R4 is adjusted until the ratio of resistance across ADB equals ACB and no current flows across C and D. Diaphragm movement changes the resistance of R3. This unbalances the bridge and causes a potential difference across C and D, which is measured. Modifications to the Wheatstone bridge. Replacement of the galvanometer with a differential amplifier. As the potential difference produced is very small, a differential amplifier is commonly used in place of the galvanometer to increase the sensitivity of the circuit in detecting the signal. Another modification is to replace all resistors R1 to R4 in the Wheatstone bridge with strain gauges to increase the sensitivity and accuracy of the system. R1 and R2 would be attached to one side of the diaphragm. R3 and R4 are attached to the other side of the diaphragm. As the diaphragm moves, the resistances of the pairs of resistors would change in opposite directions. This produces a larger output signal. However, in practice, it is very difficult to attach 4 strain gauges to a small diaphragm. Ohm's law. This states that the electrical potential V equals current I times resistance R, or I equals V divided by R, where V is voltage, I is current, and R is resistance. R may represent resistance or impedance depending on the type of circuit being used, either AC or DC. The strength of an electric current varies directly with the electromotive force voltage and varies inversely with the resistance. This equation can be used to calculate any of the above values when the other two are known. Magnetism refers to the attractive and repulsive forces between objects caused by the movement of electric charge. An electromagnetic field is produced when current flows in a wire. Two wires with current flowing will exert an attractive or repulsive force upon each other as adjacent magnetic fields interact with each other. Capacitance. Capacitance refers to the ability of a capacitor to store electric charge. It is measured in farads. Charge C equals capacitance F times voltage V. A capacitor with a capacitance of 1 farad will store 1 coulomb of charge when 1 volt is applied to it. The electric charge on either plate of a capacitor is proportional to the voltage across the plates. Most capacitors measure in micro or picofarads, as 1 farad is a large value. Stray capacitance. This is capacitance that is not designed into the system, but is incidental to the construction of the equipment. Capacitors. These are passive electrical components that store electrical energy. Structure. It consists of 2 terminal plates separated by a non-conducting substance, the dielectric. Mechanism of action. Capacitors store electrons after the application of a potential difference. When electrons flow onto a plate of a capacitor, that plate becomes negatively charged. The electrons of the adjacent plate tends to be driven off via repulsive forces. When the first plate becomes full of electrons, no further flow of current occurs. Current flow ceases and the rate of decay of current is exponential. The amount of charge a capacitor can store is determined by the dielectric material used, the dielectric constant. The amount of charge is also proportional to the size of the plates and inversely proportional to the distance between the plates. Current only flows when the polarity is reversed. Electrons are now attracted to the positive plate. Electrons then flow off the negative plate. Capacitors in a DC circuit. These curves occur if current and charge are measured in a circuit that contains a capacitor at the moment when the switch is closed to allow the flow of DC. The charge at the negative plate of the capacitor accumulates until maximum capacitance is reached, resulting in cessation of current flow. There is an exponential decline of DC to zero. The majority of current flow occurs through a capacitor when the current is rapidly charging. Capacitors in DC circuits causes increased resistance to current flow. There is an exponential increase of charge. Capacitors in AC circuits. Capacitors allow the flow of AC in preference to DC. AC current can flow through the capacitor as the alternating direction of current flow prohibits a significant build-up of charge in one of the plates. Mean current flow is highest for high-frequency AC, followed by low-frequency AC, followed by DC. There is less time for current decay before the polarity is reversed. This graph shows the current change in a low-frequency AC circuit when there is a capacitor. When the current flow is positive, the capacitor behaves as in a DC circuit. However, the capacitor generates a curve that is inverted compared to the first when current flow reverses polarity. Current reduces exponentially when passing through the capacitor, thus mean current is low. This graph shows the current changes when a capacitor is placed in a high-frequency AC circuit. There is less time for exponential decay of current as AC polarity alternates rapidly. This causes the mean positive and negative current flows to be increased. Impedance of a capacitor equals the distance between the plates divided by current frequency times plate area. Inductors. An inductor is an electrical component that opposes changes in current flow by the generation of an electromotive force. Structure. It consists of coils of conducting wire wound around a ferrous or air core. A metal core will increase its inductance. Mechanism of action. Inductance. Inductance is a measure of the ability to generate a resistive electromotive force under the influence of changing current. This process occurs when electric current flowing through an inductor creates a magnetic field around it, which creates an electromagnetic force which opposes the original current flow, known as the back EMF. Electromotive force is an analogous term to voltage when considering electrical circuits and components. The SI unit for inductance is Henry. Henry equals voltage times time divided by ampere. When the rate of current change is 1 ampere per second in a circuit, an inductance of 1 Henry would generate 1 volt across the inductor. Inductance can also be defined as Henry equals Weber divided by ampere. 1 Henry is the inductance when 1 ampere flowing in the coil generates a magnetic field strength of 1 Weber. Inductors in DC circuits. Inductors allow the passage of DC and low-frequency AC much more freely compared to high-frequency AC. Resistance to current flow increases initially when the magnetic field is establishing and decreases to negligible levels once the magnetic field is established. This graph shows current and back EMF trends when an inductor is placed in a DC circuit. Current increases with time and is represented as a built-up exponential curve. The rate of change of current is highest initially after the inductor is connected to a DC source, and thus a high back EMF is produced. An instantaneous jump in current is blunted by this initial high back EMF. A steady-state current flow is eventually achieved as the back EMF reduces. The back EMF decreases with time and is represented as an exponential decay curve. When there is greatest change in current flow, back EMF is greatest. The amount of current passing through an inductor is minimal. Inductors thus act as high-frequency filters as they tend to oppose the flow of rapidly alternating current flowing through it. Inductors in AC circuits. Reactance rises in proportion with the frequency of AC. This occurs as the repetitive creation and reversal of magnetic field produces a constant back EMF resisting current flow. Back EMF generated is proportional to the rate of change of current passing through an inductor. If an inductor is in the circuit, the flow of current is prolonged for a short period when the power is switched off. This occurs because when the power is switched off, the collapse of the magnetic field induces a flow of electrons in the inductor and the circuit for a short period. Reactance. The definition is the opposition to flow of alternating current. It is measured in ohms. Capacitors and inductors both exhibit reactance. Reactance of a capacitor. AC current can flow through capacitors as the alternating direction of current flow prohibits a significant build-up of charge in one of the plates. Capacitive reactance reduces in proportion with AC frequency. It is easy for higher frequency AC to pass through a capacitor. Capacitors can thus be used to filter out low frequency AC and DC currents. Reactance of an inductor originates from the back EMF generated within the coil. The repetitive creation and reversal of magnetic field produces a constant back EMF resisting current flow. Inductive reactance rises in proportion with frequency. It is difficult for higher frequency AC to pass through an inductor. Thus, inductors can be used to filter out high frequency AC. Inductors moves out the effects of power surges in monitoring equipment. Impedance. Impedance is defined as the sum of all the forces impeding electron flow in an AC circuit. It is also defined as the total of the resistive and reactive components of opposition to electrical flow, which includes resistance and reactance, where resistance refers to the opposition to flow of direct current and reactance refers to the opposition to flow of alternating current. Impedance is measured in ohms and consists of ohmic resistance, the real part, and reactance of the inductor or capacitor, the imaginary part. Magnitude of impedance for a given resistance and reactance is equal to the square root of the sum of the squares of the resistance and reactance expressed in ohms. Unlike resistance, impedance is dependent on frequency. Impedance includes that produced by resistors, capacitors, and inductors. Impedance through capacitors and inductors is related to the frequency at which AC reverses direction. Impedance is directly proportional to the frequency times the inductance. Impedance is inversely proportional to the product of the frequency and the capacitance. Insulators are high impedance devices. Conductors are low impedance devices. Electric circuit. This is a closed path of conductors and electrical components in which electric current flows under the influence of a voltage or current source. Substances that allow a charge to move through them can be classified as conductors, insulators, and semiconductors. Conductors are substances that allow electrical charge to move freely through their structure. The outer electrons of the atoms are loosely bound and free to move through the material in response to an electrical potential difference. Conductors have low impedance. An example would be copper. Insulators are substances that do not allow electric charge to move freely because their electrons are more firmly bound. These have high impedance. Examples include rubber, glass, and wood. Semiconductors are substances that have a conductivity between that of an insulator and conductor. For example, silicon and germanium. Semiconductors are used widely in electrical components such as solar cells, transistors, thermistors, and light-emitting diodes. Electrical circuits can be classified as series circuits and parallel circuits. In series circuits, there is only one route for the flow of electrons between the negative and positive terminals. For parallel circuits, there are multiple routes through which electrons can flow. The proportion of electrons taking each route depends on the resistance of each route to the flow of current. The lower the resistance of a route, the higher the proportion of electrons flowing through it. Load refers to the amount of current flowing through a given device. A small load occurs in a very high impedance circuit, which allows only a small current to flow. A large load occurs in a low impedance circuit, which allows a large current to flow. Short circuit. A short circuit occurs when there is a zero impedance load with a very high current flow. These are the symbols of common electric components: alternating current, direct current, switch, cell, voltmeter, ammeter, capacitor, transformer, resistor, variable resistor, motor, battery, earth, inductor, and lamp. Generation and distribution of electricity. Generation of electricity. Electricity is produced by alternators, also known as electrical generators in power stations, and distributed by a system of conductors. Three-phased AC produced in a power station. An alternator consists of a rotating magnetic core surrounded by stationary windings of a conductor. Magnet rotation results in a fluctuating magnetic field. The fluctuating magnetic field induces an electromotive force in the surrounding windings. This electromotive force moves the charge present in the wires of a circuit. The electric current varies sinusoidally, aka alternating current, due to the fluctuating nature of the magnetic field. Three-phase alternators are used in the power station. They consist of three sets of windings that are 120 degrees apart, surrounding a rotating magnetic core. Three sinusoidal waveforms are produced by these alternators, which are out of phase with one another by the time taken for the magnet to rotate 120 degrees. The frequency of mains AC current varies according to the country. In the UK it is 50 Hz, in the US it is 60 Hz. 50 to 60 Hz is used as higher frequency causes greater power loss through transmission lines, and lower frequencies cause a detectable flicker from light sources. Distribution of electricity. Three-phase AC leaves the power station via three wires, one for each phase of AC, to enter a step-up substation. Transformers then converts the power station output to 155,000 to 765,000 volts for transmission in high voltage power lines over long distances. Power losses in the grid are related to current flow, not voltage. High voltages maintains efficiency for transmission and distribution of electricity. As electricity approaches the end user, it passes a series of step-down substations. Voltage is decreased to about 10,000 volts for distribution to substations close to the users. Subsequently, voltage is further decreased to 240 volts in each of the three phases. One limb from each phase of the three-phase AC leaves the transformer to join at the star point to form a neutral and ground common to all three. The other end of the circuits for each phase are used to supply the electric current in a live wire to properties within the range of the substation. The electric current in the live wire entering a property is of a single phase. From the substation, the current travels in two conductors, the live wire and the neutral wire. The live wire has a potential of 240 volts and carries the potential to the equipment. The neutral wire is connected to the earth at the substation. This keeps its potential approximately the same as earth and returns the current back to the source, completing the circuit. Function of transformers. According to Faraday's law, this describes how alterations in a magnetic field around any closed circuit will generate an electromotive force to cause current flow. The greater the change in the magnetic field over time, the greater the electromotive force. Transformers transfer electrical energy between two circuits by electromagnetic induction and consist of two sets of windings around a ferrous core, the primary winding and the secondary winding. Vp divided by Vs equals Np divided by Ns, where Vp is the primary coil voltage, Vs is the secondary coil voltage, Np is the number of turns on the primary coil, and Ns is the number of turns on the secondary coil. AC flow in the primary windings induces a fluctuating magnetic field. This creates a fluctuating magnetic flux in the ferrous core and induces an electromotive force in the secondary windings, causing current to flow. The output voltage is determined by the ratio of the number of coils between the primary and secondary windings. Grounding. In electrical terminology, grounding is applied to two separate concepts: grounding of electrical power and grounding of electrical equipment. In the home, electrical power is grounded and electrical equipment may or may not be grounded. In the operation theatre, electrical power is usually ungrounded and electrical equipment should always be grounded. In the home, Utility companies universally provide grounded electrical power as a safety measure to prevent electrical charges from building up in their wiring during electrical storms, and as a preventive mechanism against the very high voltages used in transmitting power by the utility companies to enter the home in the event of an equipment failure in their high voltage system. When there is no equipment ground wire, only one additional contact point is necessary to complete the circuit and thus receive an electric shock. Electrical current preferentially flows along the low resistance ground wire when a faulty equipment that contains an equipment ground wire is properly connected to an electrical outlet with a grounding connection. The individual touching the hot wire while standing on the ground still completes the circuit, but will only receive a small current flow through that individual. 120 volts in the USA and 240 volts in the UK potential difference exists between the hot and neutral wires, the hot and ground wires, and the hot wire and the earth. In the operation theatre, an isolation transformer converts the grounded power on the primary side to ungrounded power system on the secondary side of the transformer. 120 volts potential exists between lines 1 and 2 in the US. There is no direct connection from the power on the secondary side to the ground. The equipment ground wire is still present. These are my references. Thank you.